Alright, so today we'll be continuing our study of differentiation, and we will be doing so by looking at some inverse trigonometric curves. So, the inverse trigonometric part comes from sine inverse. You've probably seen this before. This is just an inverse sine. You've done this probably a million times in trigonometry, putting this into your calculator. But now, what happens if we try and differentiate it? Well, we actually get this really weird expression, which is 1 over the square root of 1 minus x squared. Now, you don't really need to know where this comes from. You don't need to know the proof of it off by heart, and you'll never be questioned about the proof of it. You just need to know that this is the case. So when we differentiate inverse sine, we're going to get this expression. And in fact, this will be on your formula sheet. So while you need to know it and know what it looks like, if you forget some little bits about, oh, is that a plus sign or is that a minus sign, you can always refer to it. But it's always good to know these formulas because you don't want to be looking them up every time you're in an exam and one of them comes up. But yeah, so we just have to know that the inverse of sine is 1 over the square root of 1 minus x squared when we differentiate it. And so now let's look at an example of using this. So we want to find the equation of the tangent to the curve y is equal to inverse sine of x at the point 0, pi on 2. Now, what are the two things we need for a tangent? Well, because a tangent is a straight line that connects with a curve at one point, we need to find the straight line. And in order to find a straight line, we need a point that it passes through, which is exactly what we've got here. And we also need the gradient. Now, how do we normally find the gradient of a function? We differentiate it, and then we substitute in the values for that point, and that gives you the gradient at that point, which is something you should be very familiar with by now. So now if we want to find the gradient, let's do that. So in order to find the gradient, we start with y is equal to sine minus 1, because that's our function. So now let's differentiate our function. So using the formula that we just learned on the previous slide, the derivative of this is going to be 1 over the square root of 1 minus x squared. And so now, in order to find the gradient of the tangent at this point, we're going to have to substitute in the 0. So when we substitute in the 0, what we're going to get is, we sub in 0, then this gives dy dx is equal to 1 over square root of 1 minus 0 squared. That 0 squared just stays 0, so we're not subtracting anything. So it's going to be 1 over square root of 1, and square root of 1 is just 1. So this whole fraction just becomes 1. So that's actually a really easy gradient, because it just means we have a gradient of 1. So now, if we want to make the equation, this bit should be nothing new. This should all just be stuff you've been over through a bunch of times before. What we're going to do is we're going to use the 2-point formula. Sorry, not the 2-point formula, the point gradient formula. And so that is y minus y1 is equal to m outside of x minus x1. It's where our x1 and our y1 come from this point, which I'll clear up a bit. And the m is just the gradient we found. So this becomes y minus our y value, which is pi on 2, equals to 1, which is our gradient, brackets x minus 0, because that's our x value. And so that becomes y minus pi on 2 equaling to, that doesn't matter because that's just 0. 1 times x is just x. So we get y minus pi on 2 is equal to x. One last step, y is equal to x plus pi on 2. That way we have our y by itself, and now we've got our gradient, which is 1, and our y-intercept, which is pi on 2. So that is the equation of our tangent at the point 0, pi on 2 for y is equal to sine x. So this is really easy. We just had to use the formula, and then we just had to use this formula here for the derivative, and then it's just working through the rest of it. You don't need to know anything else about this formula other than how to use it in these sorts of situations. So it's actually really easy to learn. Now, there is a little bit of an exception to this rule, and that is if we have something divided by this x. So sorry, something dividing this x. So this a value is just a constant. It can be any constant it wants. It could be a whole number like 2, 3, 4. It could be a decimal, it could be negative, or it could be a fraction. And we'll look at some examples. But the only difference is that if we are dividing by something here, instead of having 1 squared, it's just whatever we're dividing by squared. And importantly, it's what we're dividing by, not what is out the front of the fraction. So if this was, say, 2x, we would actually be dividing by a half, which acts to double it. We wouldn't be doing 2 squared, it would be a half squared. So let's look at some examples of how to use this formula. So if we want to differentiate sine minus 1, x over 3, then the derivative of this is just going to be 1 over square root, and now we're just squaring the thing that's dividing, which is our 3. So that's 3 squared minus x squared. So that becomes 1 over square root of 9 minus x squared. And because of this minus sign, we can't actually really simplify this anymore, unless we were to split this up, but this is about as simple as it gets. That's only going to complicate things more. So that is how we use that for sine. Now, if we move on, we'll note that there is in fact formulas for both for cosine, and we'll look at later. There's also going to be one for tan, as you've probably expected by now. So for cosine, it is the exact same formulas, the same two formulas, except there is a minus sign, which pretty well makes sense because normally when we differentiate or integrate cosine, it's just going to be pretty much the same as sine, except we're now working with negatives and we have to be mindful of where the negatives are. So again, it's just the same formulas, the exact same formulas we just used, except now we've got a negative. And so if we're looking at an example here, if we want to differentiate this, it's just going to be 1 over, importantly, negative 1 over square root. Now, we want minus x squared, but we want to square here the thing that's dividing the x. So we're not going to put 2 here, it's not going to be 2 squared because we're not dividing by 2, we're timesing by 2. And what's the same as dividing by 2? Sorry, timesing by 2? It's dividing by a half. Because if we divide something by a half, we're effectively doubling it. And so we're going to actually do a half all squared there. And so this is going to become minus 1 all over square root a quarter minus x squared. And that's it. That's your integral. So that's exactly what we want. And we're done for cosine. Now moving on, looking at tan, the rule is really similar, but just slightly different. It is equal to 1 over 1 plus x squared for the base case, or we replace that one and this one with a, except this bottom one's actually a squared. So it's really similar, except now we don't have a square root on the bottom, and we're including a on top, not 1, and we're also adding in the middle. So if you just pay attention to those few little things, you should be fine. But again, if you forget these formulas or you start mixing them up in your head, or you don't remember if it's the sine or the cosine that has the negative sign, these are on the formula sheet, so feel free to refer to them in exams, but it's always better to know them. That way you don't have to refer to them. So if we try and differentiate this, then when we differentiate this, it's just going to be a on top, which is 5, because we're dividing by 5, all over a squared, which is 5 squared, plus x squared, which is just x squared in this case. And so this is our derivative. And so if we simplify this, this is going to be 5 over 25 plus x squared. And you're done. And just like with the sine example, with each of the cosine and the tangent examples that are both inverse, we can then find tangents to these curves. I know the tangent of the inverse tangent, it sounds a bit weird, but we can find tangents to the curves. We can use them to find derivatives for any curve like this. We might have to use the product rule or the quotient rule involving these. You just have to treat these like your normal differentiation. So we use the same things with logs and exponentials. These are just another tool that you'll be asked to differentiate throughout. And again, just like everything else you do in differentiation, it's just a matter of learning the formula and the method, and then you'll be fine. And again, these are on the formula sheet, so if you really forget, you can always look there for them. Anyway, I hope this lesson was helpful, and I hope to see you guys next time.